Good morning. I'm Jeff Hammond, Executive Director with IGSHPA. Thank you very much for joining our Dig Deeper webinar this morning. We have a special guest, Brock Trimble from SHARC Energy Systems, and we're excited to go through this presentation. Great information. Before we get started, I do have just a couple of slides to go through, just to update everybody, make sure that you know all the latest that's going on with IGSHPA, and I'll introduce Brock and we'll be ready to go. All right, so I'd like to talk just a little bit about our 2022 IGSHPA conference. If you were on the town hall in January, you already heard about this, but some people may not be aware of it. And also wanted to give you an update on renewals and CEUs. This Dig Deeper webinar is eligible for CEUs, for IGSHPA CEUs. The annual conference that we're excited to announce is, again, partnering with NGWA. So IGSHPA is working with National Groundwater Association. We had a very successful conference in 2021, and this is usually NGWA's largest conference when it's hosted in Vegas. So that'll be in December. It's already on the website. If you go to igshpa.org, you'll find information about registration and also for exhibitors. So check that out, and we look forward to seeing you in December in Vegas. Just a note here on CEUs and renewals. We had suspended CEUs in 2020 and 2021. We're no longer waiving those for 2022 renewals and accreditation certifications. Keep in mind, though, they're going to be easier to get now. The Dig Deeper and town halls are eligible for CEUs. Each contact hour is worth 0.1 CEUs. It is important if you'd like CEUs for this Dig Deeper webinar that you let us know. Just simply send a chat message to IGSHPA and include your name and email address. We'll keep track of those CEUs. Once you accrue 0.5 CEUs, and we'll send out a certificate. If you have any questions, you can always contact us at info@igshpa.org. if you have any questions about your CEUs or how many you have. But please send a chat message, and we'll have that on record. Just a little bit of housekeeping. We will be having a question session after the presentation. Please add your question to the chat feature in Zoom, and then I will be reading those questions at the end of the presentation, and Brock will be able to answer all the questions. If we don't get to your message, we'll do our best to get back to you just as soon as possible. A couple of other notes here. As you probably saw on your screen, this is being recorded. So you'll be able to view this session later on, or if you have colleagues who weren't able to make it today, they will be able to go to our YouTube channel and watch this presentation. Also, please mute your microphone unless you're speaking. That is a little distracting to the speaker as well as to everyone who's participating. So if you would, that would be super helpful. And on to our speaker. Brock Trimble is the Director of Technical Sales with SHARC Energy Systems, a Canadian-based wastewater energy recovery equipment manufacturer. Brock is a certified Red Seal plumber and has over a decade of hands-on application experience and system knowledge with wastewater energy transfer systems. Brock has been involved in a range of projects of various sizes and applications, from initial design concept through equipment manufacture, installation, and ongoing operations. So with that, I will stop sharing my screen and turn it over to Brock. We're excited to have you here, Brock. Thank you very much for taking the time to do this presentation.
Sorry, thanks, Jeff. I just realized I was muted. Thank you so much for the introduction and to the group here at IGSHPA. It's a pleasure to be speaking with you all today. As Jeff mentioned, my name is Brock Trimble. I'm the Director of Technical Sales for SHARC Energy. I have been with the company basically since the beginning. And as Jeff mentioned, I'm originally come from the mechanical trades. I have been involved with building, installing, maintaining this equipment from the very beginning before moving up into the more of an office setting and leading our teams in on the technical side. So hopefully by the end, I'll be able to answer any questions you have. If there are any further questions after the presentation and once the time is up, we'll be more than happy to follow up with this team afterwards. So with that, I'm going to turn off my my video, and just allow you to view the screen. So as Jeff mentioned, we are SHARC Energy. We are founded in a little industrial suburb just outside of Vancouver, BC, Canada, called Port Coquitlam. We've been around for a little over a decade, founded by a group of professionals with a ton of experience in the HVAC, geo-exchange, and plumbing mechanical industries. And with this, the primary goal of what we did to start off with is realizing that there is a ton of energy available in wastewater, and that if it can be taken and put back into buildings and energy systems, it can have a huge impact on the overall energy use, the fossil fuels, and otherwise the greenhouse gas emissions that would typically be emitted from these types of projects. So with that, we developed our first product, which is called the SHARC, in 2011. And beyond that, we've recognized the need for a little bit of smaller scale equipment for smaller applications. So we developed what we call our Piranha, and beyond that, our Piranha HC, which is sort of an extended range version of the Piranha. So I won't get too much into the details of any of these. We want to cover the broad scope concepts of wastewater energy recovery and wastewater energy transfer, and how they can pair with geofields and geo-exchange systems. So with that, just a couple of average statistics. So the average person uses around 24 gallons of hot water per person per day at 140 degrees Fahrenheit. If you think about all of the uses that you typically have with water throughout your day, showering, washing your dishes, clothes, using lavatories, kitchen sinks, all of that stuff, as well as going to restaurants, cafes, laundry facilities, any of those types of things that we all rely on for our daily life, all of those use hot water and discard it down to the sanitary sewer. All of this has an incredible amount of energy that we can start to recover and capture. The average residential wastewater temperature leaving a single multifamily building is usually between 70 to 72 degrees Fahrenheit. And on larger applications, more commercial and industrial, that wastewater temperature can be significantly higher, reaching up to 140 Fahrenheit or even higher. So all of that gives a really, really great energy source that we can start to use to put back into the buildings and to supplement and offset any loads that may be used through geothermal systems. So supporting that use of geothermal with an additional energy source. And I'll get into how all of this occurs as we go through the presentation. Now, as we look for wastewater sources, we typically look for black or gray water from within individual buildings, and on a broader scope, looking at sanitary sewers or end-of-line points like lift stations and treatment centers to collect really, really large volumes and energy sources that can serve the broader and much larger scale applications. So wastewater is a heat pump source. Why do we want to use it? Well, you can see here there's a couple of items on this chart. This the main chart is from an area in Toronto where they were looking to compare the air source, geothermal, and wastewater sources across for a project. So what they found is that utilizing geothermal as their primary source, wastewater has this really nice stable temperature that can be used to supplement and offset that geothermal. So with this, as I mentioned previously, standard multifamily residential projects see a little bit more stable temperature throughout the year as it's exiting the building itself. And there's another great example of the Denver Municipal Sanitary Sewer in Colorado that sees an overall average temperature of around 65 degrees throughout the year as it's passing through a number of the city sewer trunks. So with this sort of range of temperatures, it has a really great stabilizing effect and supplementary nature when it comes to that geothermal tie-in. Using these temperatures to add energy into a geothermal field when that field is at a low temperature, or being able to take temperature out of the geothermal field when it's at a high temperature. So looking at the overall kind of style of heating and cooling ranges with the typical wastewater range, what you're going to see here is that there's a really incredible potential for the movement of energy. When we look at typical cooling applications, they will typically see energy that needs to be rejected from a project between 80 and 100 degrees Fahrenheit or so. The average temperature of wastewater typically sits within that 65 to 75 degree range. So there's a lot of energy potential to move from the building cooling source into wastewater and reject it out into the sanitary sewer. The same fact can be looked at when we looked at the wastewater range and then the typical heating load. So when you're looking for heating applications that would typically draw from your geothermal field and take that field temperature down, we can also add that wastewater energy into the field, increasing the field temperature and having a really great effect on the heating application so that we don't draw that geothermal field down to a temperature that is essentially too low to really operate efficiently. So looking at that, we have a little chart here to show thermally optimized condenser water systems. So you can see over the seasons how the big swing can occur when you're looking at geothermal fields, otherwise boiler systems, and then finally wastewater temperatures. So this is just one quick example that we have for a geothermal field that over the seasons we'll see roughly a 40 degree Fahrenheit swing. It can be even higher or lower in that case and see a bigger overall delta T. Now with boiler backup, you might be able to realize a little bit of a smaller overall delta T, but the ideal situation is to pair that geo with wastewater, and you'll see a much tighter delta throughout the seasons, impacting the overall performance, efficiency, and stabilized field when it comes to looking at that geothermal source. So why wastewater? One, essentially, it is a limitless source material. It's always flowing out of our buildings, beneath our feet, and out through our sanitary sewers, and it's just waiting to be captured. With wastewater, we also see a very constant temperature and consistent temperature throughout the year. Because most people still use their the hot water for their applications at generally the same temperatures throughout the year, we don't see too much of that variation when it comes to seasonality or geographic location. And all of this lends itself to a really stable and usable energy source throughout the year. So with that, we can have a big impact on the overall energy loss from buildings and what you can put back into or pull out of the buildings, as well as reducing to a big degree the amount of GHG emissions that would otherwise be emitted by having backup boiler or fossil fuel natural gas style boilers. What we're also seeing is a really big market demand, and this group is going to be very familiar with low carbon emission energy sources. And of course, that is leading towards electrification, and with that, high efficiency electrification, meaning the use of heat pumps and a number of these types of renewable and reusable energy sources. With this, we see a lot of local legislation that is pushing the use of all of our types of equipment to meet energy targets.
Brock, I think you may have muted yourself.
My apologies. Where did I drop off?
Just after the local legislation.
Okay, perfect. Sorry, I must have tapped something on my keyboard. I was just going to say what we see in locally in British Columbia, Canada, and in a number of jurisdictions throughout North America, is that there are also incentive programs that are pushing the use of all of these highly electrified and highly efficient sources of energy to the forefront in order to meet those targets and goals. So with that, there are a few solutions on the market for both small scale energy recovery as well as large scale energy transfer. Now I'm going to go through both of these in a little bit of detail and specifically discuss how we can look at recovery versus the transfer when it comes to scaling opportunities. So small scale energy recovery is really going to target individual building applications, and these are going to be small to medium scale multifamily residential, as well as the small to medium scale commercial and industrial. And when we start getting into larger scale applications, we can look, excuse me, a little bit more at energy transfer, that energy from sewer into buildings, or from buildings out into sewer and geothermal fields. So we look at this typically when we're looking at medium to large scale multifamily residential, which are going to be either typically large scale single buildings or multi-phase build outs, as well as medium to large scale commercial and industrial projects, and finally looking all the way up to scale to district heating and cooling networks serving large parcels of land. So first, we're going to look at the small scale energy recovery. And you can see here a number of the different types of applications that can be served: multifamily, dorm style student housing, community housing, et cetera, hospitals, hotels and hospitality, as well as a few of these other sort of minor applications. Community activity centers, government owned buildings are a really great application to serve as well. So with the smaller scale wastewater energy recovery type of projects, there are, excuse me, wastewater source heat pumps. Now, a wastewater source heat pump is everyone's going to be familiar with the technology behind heat pumps, but this is a specially designed heat pump, self-contained, that has a specially designed direct expansion heat exchanger that can recover energy directly from wastewater and put it into the refrigerant circuit in order to output hot water into your buildings. Now, what we typically look at when pairing with geothermal applications is a dual source wastewater source heat pump. And this has the ability to combine not only recovering energy from wastewater, but also taking energy from a geothermal application in order to use both sources to output domestic hot water, or hot water for any other hot water demand that may be seen within the building. So using this during cooling dominant months, the heat pump can take energy from the geothermal source and use that as its dominant source for energy recovery to put hot water into buildings. This can help to offset a little bit of the load on the geothermal field as it's doing all of that cooling and putting energy and into the field and increasing that field temperature. During the heating dominant months, the heat pump can take its primary energy source from a wastewater source. So using this, we can offset the heat demand that would otherwise be seen from the geothermal source as well. In this, it will, by not pulling all of that domestic hot water heating energy from the geofield, it allows more energy to be used for the building heating source, as opposed to, taking all of that energy for the building. Having that energy sharing can really have a positive impact on the overall design of the system. So with this, these heat pumps can often see a much higher efficiency than a single source heat pump alone, and can use the highest source temperature, depending on seasonality and application, to drive the overall COP of the hot water heating output. So just in this slide, you're going to see basically the overall inner workings of a heat pump, fairly standard, just with a little bit of a different twist by using that wastewater and then the additional geothermal source. So everyone's familiar with the overall use of a heat pump and a compressor system: drawing energy from a source, putting it into the refrigerant, using the compressor to boost the temperature and the pressure within the refrigerant, and sending that energy into a condenser, outputting hot water, which would be used for many uses within the building. In this type of heat pump, it's can actually be a dual refrigerant circuit, utilizing two evaporators. The first, which is paired with our wastewater source, taking energy from wastewater and again absorbing that energy across the wall of the evaporator into the refrigerant circuit to be used for that hot water output purpose. Now, having the second evaporator allows for that secondary tie-in to the geofield, utilizing that energy when appropriate and when most applicable to pull energy from the loop, use that as the source in the refrigerant circuit, boosting again with that compressor and outputting hot water. So with these types of systems, there's often settings that you can use for determining which is going to be your primary source, either wastewater or your geofield, or you can do combined and allow them to simultaneously operate using the unit to control expansion valves and other pieces of equipment in order to direct the refrigerant flow to the ideal source, and again, boosting that overall energy efficiency through the COP in order to output hot water into the system. So in terms of an overall installation type of scenario, what we typically see is the wastewater source heat pump is going to tie into a wastewater holding tank, and this will act as basically a big thermal battery, very similar to what you would all see with a geothermal field, right? You want to use the ground as a battery for energy. We use a wastewater holding tank to collect as much wastewater outflow from a building or from a sanitary sewer as possible, utilizing that energy when necessary. So as the wastewater source heat pump works, we feed wastewater, liquid wastewater, and all of that energy into the evaporator, pull the energy out, and of course, produce that hot water, ultimately allowing the wastewater source to flow downstream and out to the city sewer. So really just using that wastewater as a temporary energy source before it continues down the line. And this is really great because with the use of wastewater, it's constantly refreshing itself with energy and fluid. So we don't have like a stagnant source of wastewater that we would either deplete or oversaturate with energy typically. It becomes that really, really great stable source to draw from throughout the day. And then utilizing the secondary source when it comes to that geothermal field and the secondary evaporator, we would tie in through a hydronic line to the geofield, and again draw energy out of that field when applicable, taking a load off of the field, using that energy as the source to output domestic hot water. So again, both of these types of systems can be used in tandem or independently, depending on demand and seasonality, in order to drive the overall efficiency and effectiveness of wastewater, geothermal source, and hot water output. So that covers the small scale energy recovery type of application. And next, what we're going to look at is the large scale energy transfer. So what you'll notice here is that a number of the applications are very much the same as what we see for the small scale, of course, just in a much larger scale application. So larger multifamily, dorm style student housing, community housing, et cetera, hospitals, hotels, motels, community centers, and again, being able to scale all the way up to district energy type of applications. So this type of equipment is typically more of a wastewater filter. So a wastewater filter allows access to the thermal energy contained within wastewater by temporarily removing the solids from wastewater. We filter and remove the solids and allow all of that filtered wastewater to pass through a downstream heat exchanger, where all of that thermal energy can be transferred to or from a building and a geofield in order to provide both energy recovery and energy rejection potentials. So with this, there are a few different types of equipment like this on the in the market, only a couple though. And what we see is that there are different sizes and scales for these. So for example, this type of wastewater filter has 3 different sizes. And you can see here it has different port sizing. So 6-inch, 8-inch, and 12-inch inlet and outlet ports. And with increasing pipe diameters, we also see increasing flow rates. So more flow in here with using filtration and passing that flow through the downstream heat exchanger. You can see how those typical energy transfer numbers can really start to climb and increase as you're using more and more wastewater as your source. And of course, with these types of units can be installed in parallel, so multiple units side by side to increase the overall flow rates, filtration, and energy transfer available. And I will note that is the same for the smaller scale energy recovery options as well, multiple units side by side, increasing the overall capacity for the system. So with wastewater filters and energy transfer, the energy can be extremely variable in its use. Once the energy has been transferred into the geothermal field, it can be used as a source, what everyone will be familiar with, source for domestic hot water heat pumps. It can be used for space conditioning, so energy recovery for heating applications, energy rejection for cooling applications, as well as providing wastewater cooling for more commercial and industrial applications, taking energy from wastewater and putting it into the geothermal field at a really high degree, especially during those winter and heating months. And of course, what we really want to focus on is that geoloop conditioning. And what we've seen is also geofield offset. So by using wastewater as this supplementary type of energy moving into and out of a geofield, we've been able to see studies where the geofield can actually be downsized using less boreholes, less land space, less overall cost, but with the same positive effect that we want to see with that geothermal application. So with this, I like to refer to the wastewater filter type of system as being exponentially efficient by transferring energy into these low temp style or ambient temp style loops. And this is because, as you saw on the previous slide, we can transfer up to megawatts of thermal energy for very, very low kilowatt energy input. Usually only a couple of small scale motors that are used to operate the equipment, provide that filtration, and see that very, very large scale thermal transfer into your systems. So overall, a wastewater filter system would look something like this. Typically controls for the filter system, piping and valving, and then a paired plate and frame heat exchanger that would be used as that actual interaction to move energy from wastewater and into the geothermal field and the building source. So the next couple of slides that I have here are going to be used to illustrate both energy recovery and energy rejection as a concept, and then I'll show you how it will sort of tie into that overall geothermal field concept. So what we look at is, again, one of two ways of moving energy, either moving energy from wastewater into a building or a geothermal source, or the flip side, moving energy from geothermal or building into the sanitary sewer to provide energy rejection. So this slide here shows energy recovery, and I hope everyone will bear with me as we just show sort of the color coding for warm and cold, just to really show how that energy transfer works. So in the concept where we're looking at energy recovery, the return line, or the line moving into the heat exchanger on the load side, so what we would typically look at as the building or the geothermal, will come in at a cooler temperature than the wastewater. Now, as the system operates, wastewater will be moved up and through the system. First, typically there's some sort of a maceration or a grinder to take down any of the larger diameter particulate in wastewater, because this is really what we need to remove when it comes to that filtration. So as the larger solids are broken down, they move into a wastewater filter that will remove the filtered solids and either send them back to a holding tank or downstream to city sewer. And the filtered wastewater, which has all of that really great energy potential, moves into the heat exchanger. So this is, of course, where the energy is transferred across the wall of the heat exchanger from the wastewater source and into that geofield, sending back a much warmer temperature into the field that can then be used for all of its downstream purposes. And then we return a cooler temperature down to or a cooler temperature back to the wastewater source once that energy has been absorbed. So typically the heat exchangers are sized roughly for a 10-degree Fahrenheit delta. There's a bunch of different ways that you can look at this: higher, lower deltas, different approach values, in order to make sure that you're feeding enough energy into the loop as you need. Now, the next slide is where we're looking at energy rejection. So with this, it's very much the same process. All we're doing is moving energy in a different way. So in this case, again, using the color coding, the geofield or the building source is coming in at a much warmer temperature than the sanitary sewer source. So with this, we do the exact same process, move wastewater up through the system, filter the solids and get rid of them using that filtered wastewater now as the heat sink. So moving energy across the wall of the heat exchanger from your geofield or your building system into the wastewater and sending it back to the sewer at a warmer temperature. So both of these types of heating and cooling processes can be used with the same piece of wastewater filtration equipment, depending on seasonality and application. It really just depends on what the temperatures look like on either side of the loop in order to provide that supplementary energy, energy rejection, or field stabilization. So what we see in a lot of cases is getting into energy sharing, and this will hopefully illustrate the preliminary concept before I finally show the actual geofield tie-in. But in this case, what we're looking at is an overall system building loop that is looking to generally share energy. So in this case, we're probably looking at a number of different pieces of equipment within the building. You know, equipment on the south side of a building that might have a lot of thermal gain because it has some sun exposure, whereas the north side of the building will be in shade and will actually need heating. As well as domestic hot water applications. So with this, typically the geofield would just be tied in, you know, providing all of that energy source for heating, cooling, and domestic hot water. In this case, I'm just showing the wastewater access, providing energy into and out of the overall low temp building loop in order to stabilize and supplement the energy as needed. So again, as this loop begins to drop in temperature because there's a high heating demand, you can move energy from that wastewater source into the loop, providing more energy to be used. Or during cooling dominant seasons, the energy is going to be rejected into the loop, and that loop is going to start to overheat. Now, the wastewater source, again, can be used as a heat sink, moving energy from the loop into the wastewater and bringing that loop temperature down, stabilizing it, and having a really positive effect on the overall operation and effectiveness of the system design. So with all of these concepts, that is where we finally look at the actual geothermal field tie-in, in which you would have your field with a building loop, typically taking all of that energy from your field, you know, pulling energy out of the ground when it's needed for heating, putting energy into the ground as a heat sink when it's needed for cooling, and tying in that wastewater energy source. You can, again, take energy from wastewater, put it into the field and the loop when that energy level is starting to decline, or when the field and the loop are starting to gain energy and overheat, you can take that and reject it into the sanitary sewer, having a really, really great effect to stabilize the field, as well as supplement energy into and out of the overall system, extending the operational parameters of your downstream equipment, as well as stabilizing the field, making sure that it has a really nice temperature throughout the year, and also having an effect, again, being able to, in some cases, downsize the overall size of the field, as well as maintain its effectiveness over many, many, many years, where you're not overheating or overcooling the field through ongoing use. So with that, I want to say thank you to everybody. I believe that was just about a half hour. If there are any questions, I'd be more than happy to answer them.
Great, thank you very much, Brock. That was very informative. Feel free to turn your camera back on if you like, and we can start answering some questions. I'll go to the chat messages first, and I have some questions on my own. So I think we'll have some great discussion here. We'll start off. Rick has a question about one of your first slides, where I showed the graphs. He thinks maybe the entering and leaving water temperatures are backwards. Can you maybe go back to it? It's one of the very first ones.
Sorry, let me slip through here. Over here?
I can't remember exactly which one he asked that on. Rick, if you're still on the line, would you mind speaking up? Rick Clemenzi. Okay.
Oh, it does look, yeah, it does look like perhaps the leaving loop temperature should be on the low side and the entering loop should be
I think that's what he was referring to, but
flipped.
maybe if Rick will chime in, if he's still on the line. Next question from Tyler. Where are the holding tanks located and installed?
Great question. I'm just going to flip back through to these guys. So typically, when it comes to the smaller scale applications, what we often see is access to sanitary sewers from within the building itself. So this may be located in the parking garage of the building or just outside the building footprint. Depending on the wastewater access, however, it may be somewhere else. So what we've seen is with some community center applications, because we're accessing more of a city sanitary source, this might be tied in at the city sewer. So it could be a little ways away from the building itself, and then having the piping to the heating plant underground and supplying that energy into the wastewater source heat pump, and then again returning that drainage line back to the sanitary sewer.
Okay, thank you very much. Bill has two questions. First question is, how are filter media cleaned and how often?
Oh, great question. So now, again, I can only speak to our equipment, but the filter itself, there's an extraction port, again, that you can see here. So as the wastewater moves through, it's filtered through the unit, and then we actually draw it out of the bottom through a solids extraction pump and send that out and downstream to the city.
Okay, very good.
So it's constantly being removed.
Okay, thank you. Bill's next question, per unit of wastewater, what is the temperature reduction or boost in heating or cooling that acts on this effluent?
So again, typically we see roughly a 10-degree delta. However, that can be designed to a certain degree. And then if we're looking at a wastewater holding tank, depending on sizing, we actually have quite a range. So we can take that energy, the source energy down. If we see a typical entering temperature of around 70 degrees, we can take it down to, typically as low as about 41 degrees Fahrenheit. It may depend on what your field design looks like and if there are any limitations that you want to see, as well as on the high end. We've seen energy rejection as high as about 90 to 95 degree Fahrenheit using about a 70 degree entering source. So there is some variability that can be designed in for your type of project.
Okay, very good. Vondon has a question. What does the wastewater treatment plant folks think about varying input temperatures? I guess
Great
probably
question.
output temperatures.
Yeah. So when we're looking at sort of individual applications in an urban setting before they hit the sanitary sewer, there's actually very little impact on the overall system temperature as it enters into a wastewater treatment facility. So in order to really have a big impact, we would basically need to have these types of systems in every building in a city, which of course is is the goal for geothermal and wastewater source energy recovery and transfer anyways. But what we found in a couple of areas is that if they can slightly reduce the temperature of the wastewater influent that enters into the wastewater treatment facility, it actually has a positive impact on treatment, and they can save in the range of millions of dollars per year through that process.
Okay, excellent. Thank you. Bob asks, the presentation was about using a building's own effluent for heat. Do SHARC systems also work when connected to shared municipal sewer systems?
Absolutely. And sorry, that is what I was trying to drive at with a few of these slides and hopefully answering these questions as well. We do look at much larger scale applications where we look at city sanitary sewers, where we look at wastewater treatment facilities and that type of application to draw much, much larger access to wastewater and energy transfer to serve those larger project styles.
Okay, very good. Rick asks, how does efficiency compare to current plate-based sewer exchange that has been used by others?
overall typically better. And there's a couple of reasons why. So in sanitary or in typical plates sitting in sanitary sewers, there's often quite a lot of buildup and degradation of flow and thermal transfer. So there's a couple of different styles of overall wastewater energy transfer, either loops that sit within sewer piping itself. They don't see, you need really, really long runs of wastewater piping in order to have any real effectiveness. There's also a couple of different ones where they put plates in the base of sanitary sewers, and they've seen buildup of solids that, again, degrade sort of the energy transfer capability, basically create an insulating blanket over the transfer plates. Whereas this type of application, using filtering the solids, getting rid of them, and also using what I've shown here, these are backflushing valves. So as wastewater is flowing through the system, you can actually backflush automatically the heat exchanger anytime you start to see a delta T start to increase or decrease. If you're seeing pressure differentials change from design. So keeping the wastewater heat exchanger, which is a very specialized wide gap design, making sure that any small particulate passes through, there's no chance of clogging or degradation, that type of thing. By backflushing, it's ensuring that the system stays clean. Any minor buildups are blown off and sent back to the city sewer, and you maintain that overall flow rate and thermal transfer that you're looking for the lifespan of the equipment.
Thank you. Okay, the next question from John. When does this tend to make sense in terms of multifamily building size? I realize it depends, but make some statements about when to consider.
Yeah, usually this style is going to be used again in those large applications where there's a lot of wastewater flow. So typically, 3 to 4 to 500, even more. I've looked at, we have this, one of these systems, it's not paired with geothermal, but it's really effective for just standard wastewater energy recovery in a 700 unit multifamily project in Vancouver, BC. Otherwise, this type of application and the smaller scale application really serve a broad range of multifamily, and all of that energy that can be recovered can be put back into the building, into the geothermal source, what have you, in order to provide that supplementation.
Okay, thank you. Howard asks if you could discuss the pumps used.
The wastewater
side.
supply pumps, yeah. Typically they are, oh, sorry, let me jump ahead here. Typically they are just fairly standard wastewater solids handling pumps. There's a number of these on the on the market that can be used. Myers and Pentair are great brands. Sulzer, Flight. Wastewater is a big industry, so there are a number of wastewater pumps that can be used for this application, as well as grinder pumps. They're also a good option when it comes to a variety of different wastewater solids handling applications.
Okay, thank you. Bob asks, why wouldn't every multifamily apartment building in New York City adopt SHARC systems? Can you give estimates for when it makes economic sense?
Yeah, good question. So with the implementation of Local Law 97 in New York, this is actually one thing that's really coming to the forefront. Having to decarbonize to a large scale, New York specifically needs to find sources of renewable energy and electrification. So we at SHARC are actually actively pursuing the New York market. We have a rep in the area, and there's a couple of the utilities and private companies that are looking at utilities and ESCOs that are looking for opportunities to use systems like this for a number of different buildings.
Excellent. Okay. Gary asks, what is the winter average temperature of wastewater in northern cities such as Chicago?
So I don't know specifically Chicago. In Vancouver, BC, we have a project called the False Creek Neighborhood Energy Utility, which is a big district energy plant that takes its primary source for a wastewater source heat pump from a city sanitary main. And typically we see on average around and please forgive me, I'm converting from Celsius to Fahrenheit, but around 65 to about 80 degrees throughout the seasons. Sort of on the low and high end for winter and summer. Other areas will see slight variations, and it may also depend if they have combined sanitary and storm sewer systems. So there may be a small effect based on rainfall and snowmelt. So it would be best to look at your specific area.
Okay, maybe Toronto would be closer to Gary's question about Chicago.
Yeah, and what we see in Toronto, there's one sanitary main that we do have data from, and typically it's around 55 to I think 75, so roughly a 20-degree delta throughout the seasons.
Okay, great. Kathleen asks, can the dual source heat pumps be used with waste condensate instead of wastewater?
Yeah, absolutely. Typically what we see is that the condensate feeds into the sanitary sewer source anyways. So that would just add its energy to the sewer where it can be drawn from.
Okay, excellent. And we have a question from Bob. Huber and others use mechanical wipers to clear buildup on their exchange plates. Why is the SHARC approach superior to such mechanical wipers?
Well, there's a couple of different things. The SHARC systems overall see a much higher overall flow rate when we get into our larger pieces than the other types of competitive equipment. As well, with the way that we filter the wastewater, the way that we have our piping and backflushing through the heat exchanger has been very, very effective. So smaller footprint, higher flow rates, overall, better heat exchange, completely sealed systems as well, that keep all of that sanitary wastewater source isolated, nice and clean, no odors, all that kind of great stuff.
Okay, very good. And we have a question from Bill. In what climate or in what size building do you think SHARC might be used as a single system without geoloops, as a hybrid with small loop conditioning by chillers or boilers?
So typically what we see with the SHARC is that when we get, and if we're looking at the building wastewater source itself, usually around 350 plus multifamily units. Now, what we at SHARC do is try to help with assessing the overall building load, domestic hot water demand, wastewater source, that type of stuff, in order to determine whether the filtration systems or the dedicated heat pumps are the ideal way to go. So it may have, there may be some dependency on the building itself.
Okay, very good. Boyd asks, what kind of licensing will cities require of the workers who install these systems?
Not anything extraordinary. For the most part, they are, they're mechanical systems. They can be installed by plumbers. There are some electrical components, of course, that would be worked on through, certified electrical contractors. There's really nothing out of the ordinary. Again, some HVAC contractors if they need for any specific items with the heat pumps. But yeah, they're pretty standard when it comes to most of the trades.
Okay, very good. And Kathleen has a question. Do you provide 8760 temperature data for the systems to allow for modeling the geofields?
We would work with the design engineers in order to do that. We don't really work with the typical 8760, so we would give all of the information that can then be used by proper energy modelers to build this into their design.
Okay. Bob asks, if the recommendation is for 350 plus residential units, does that recommendation change if there's a gym, laundry, or other facility in the building? Do you currently serve any such multi-use buildings?
Yeah, great question. So as I mentioned, there's a 700 unit building that has one of the SHARC systems. It has a small gym facility, mostly for the residents, not a commercial space. I believe that there's a cafe and a daycare in the building as well. And then again, on the smaller side, it's a two-phase building. The second phase has around 300 units, and it uses a couple of the wastewater source heat pumps to recover its wastewater and put it back into the put that energy back into the system. So again, there's a few different items when it comes to the assessments that we would work with the design engineers on to try and assess and determine the best type of equipment for the application.
Very interesting. All right, Joe asks, in what geographic areas has SHARC achieved the greatest success, both for savings and sales?
Great question. So there's a couple of different factors on that. Our home area of BC has so far been the biggest adopter. We are seeing great success in Washington State. We have a couple of projects, both small and large scale, in Colorado. We're seeing a lot of traction in Toronto, and again, as we mentioned, beginning to pick up in New York. So really, anywhere that wastewater flows through the sanitary sewers is a good application. In terms of sort of cost effectiveness, it may depend on your area and what the motivations are. So carbon savings, if there are incentives, if there are any penalties to high carbon emissions, a lot of that type of stuff.
Okay, we have a lot of good discussion. I think this is maybe one of our most questions that we've had. Howard asks, are there any rules of thumb for installation costs?
Not that I can share at the moment. Again, it might depend on local area for labor rates, tie-ins, material, that type of stuff. But I'm sure that between us and our various rep firms, we could probably support with that.
Okay, very good. Vondon asks, I've long thought that in new construction, hot wastewater could be separated from cold wastewater to enhance recovery. Ever see this?
Yeah, so that's more of a gray water application, and we do see that from time to time. There are some different ways of doing it. If you're using gray water reclamation equipment, so trying to clarify and reuse gray water, some of the fixtures often are left out of the collection, which is unfortunate. Because items like dishwashers and kitchen sinks have a lot of hot water use that ultimately end up going to sanitary sewer when they could be used. So if there's the possibility of separating even just the water closets or the toilets, that is a fantastic opportunity. The one thing that we have learned over the years is that even water closets and toilets have a good degree of energy that can be drawn. Because if you think about it, if your toilet sits for any period of time, the water in the bowl and in the tank acclimatize to room temperature. So you're basically flushing, you're taking energy sort of out of the ambient space as it's drawn into that cold incoming water, the wastewater, and then it's just flushed down the system. So even full black water systems with toilets can be a really great application and really great energy source.
Okay. Bob has a question here. New York and Massachusetts seem to be encouraging geothermal district heating. Can you describe how SHARC might work with such systems?
Yep, absolutely. So it would pair similarly like this. Of course, this would be a much larger loop where a geofield would feed the majority of its energy into the district. And depending on what's happening, you can either have a dedicated energy plant that outputs a high temp hot water into the field. And in each of those individual buildings, they would typically have heat exchangers to draw energy from the loop for domestic hot water or heating purposes. Or if you're looking at a low temp ambient loop, the same overall principle applies. You're sending that energy out into the field, but each individual building would have heat pumps, chillers, hot water heat pumps, etc., to take energy for all of those individual uses. And when you're looking at that, you would have both the opportunity for energy recovery and energy rejection, right? So building, heating, and cooling, sending energy out into that load, into the building, sort of looking like that very similar energy sharing application, and then using the SHARC again to supplement based on sort of supplement and support the geothermal field in the event that it starts to overheat or overcool, by sending energy into or out of the loop using the sewer source as an energy source or heat sink.
Okay, very good. And Bob asks, what's the range of typical payback period?
Again, that might depend on your region. So I would advise probably connecting with our local reps when it comes to our equipment specifically.
Sure, makes sense. I do have a couple of questions for you, Brock. Because of the milder temperatures in the ground loop, when we have a system like this, do you see a reduction in equipment tonnage? Is the design engineer able to use smaller equipment for the building?
Okay, that's a great question, and probably not one that I'm best suited to answer. I don't usually get into much of the load side equipment design. But again, it can help to really increase the efficiency and the lifespan of the equipment by keeping it more within a more tolerant range, or sorry, the source energy, rather than having those big seasonal swings.
Sure, thank you. Howard has a question. Is there an on-site treatment plant, or is it better to be on the entering or leaving side of the plant?
Sorry, if the equipment is located at a treatment facility, is that the question?
Let me just read it again here. If there's an on-site treatment plant, is it better to be on the entering or leaving side of the plant? I'm not sure if
Okay.
Howard is here. Maybe he could speak.
No problem. I think I can answer. So it may depend on the treatment itself. Typically, what we see is the wastewater filtration equipment or the heat pump would be on the incoming side, and the reason is that depending on the exiting effluent after treatment, there may be some biosludge and biosolids present, and in that case, what we have seen sort of across the industry is that the bugs and the algae growth and that type of stuff can affect the heat exchangers over time. So typically we look at the pre-treatment system. If it can be after a primary or a secondary filtration, that can also assist with effectiveness. But I hope that answers the question.
Well, Bob gave us a thumbs up, or Howard gave us a thumbs up, so it must have.
Perfect.
Thank you. And Bob asks, how does one connect with a SHARC sales rep?
Feel free to reach out to us directly. You can reach us at sharkenergy.com, and we can put you in touch with our local teams.
Okay, very good. Well, I think we're just about out of time. This was a great exchange of information. I certainly appreciate your time, Brock, and appreciate everyone joining our Dig Deeper webinar. Watch your email for announcements of new town halls and new Dig Deeper sessions. If you'll go to IGSHPA.org, you'll find the events and everything that's coming up with training and conferences and so forth. Thanks again. Have a great weekend. Appreciate your time. Bye.
Excellent. Thanks, Jeff. Thanks, everyone. Enjoy your weekends. Take care.
Thanks.